Greetings and welcome to my new calculus channel. My name is John Gabriel, and today I'm going to be explaining to you quite a number of things about Hippias and his Quadratrix and Trisectrix, and also speaking about a lot of the concepts that came from those particular times. So let's begin. Now, let's get that out of the way and come right over here. So, I don't want to leave. I want to cancel. I want to be there. So this was an old applet that I modified. And I've used it in the previous 2 or 3 applets. I don't remember, but I've modified it, made it simpler, and explained a lot more things. So before I start, let's just talk a little bit about where the words Quadratrix and Trisectrix and Sectrix all come from. Well, they're all Latin words, okay? And for example, the suffix trix is feminine in Latin. So, for example, if you have, say, the word for warrior in Latin, it's bellator. And if you say the feminine version, it's bellatrix, okay? So, a longitude, you can have a trisectrix, a directrix, a longitudotrix, and I'll explain to you what that is in a moment. But directrix is what you find when you construct a parabola. So if you have perpendicular lines from the directrix to a point on the parabola and then connect it to the focus, then that distance remains the same as this distance. Okay, so this length will be the same as that length. Okay, so that's what a directrix is, and you can sort of think of it as this directrix being like one of those people who direct orchestras. What are they called again? It's such a simple word, and I can't. Maestros? I don't remember anyway. And basically, it delegates how this parabola functions. Okay, so and in this case, it's a female version. So in Greek, they have the words, for example, kabila or kabili, which is also feminine. Kabila is feminine, and it means curve. And of course, the Latin word for that is curva. And the Latin word curvatura means curvature. And of course, the Greek would be kabilotita. So, yeah, a bit of my Latin coming back there. and those are some backgrounds to where those words come from. The word quadratrix, the first part of it, the prefix quad, comes from quadrilateral, which is used for area. Okay, so quadratrix is used to calculate area. And we'll see in a while where the area connection comes in. But for the time being, that's pretty much it. You've also got, of course, another very common word that you may have heard used, which is dominatrix, and I'm not going to explain what that means. I don't want to talk about that. So the next thing I want to show you is that the sectrix of Hippias divides an angle into n equal parts, okay? And this is done, first of all, by dividing a line into n equal parts. So let's see how this is done. So if you divide, this is the angle here, okay? This angle where I'm pointing. Let me just use a pen, if I can find one. All right, here's a pen. So this is the angle. Oops, I'm sorry, it's this angle here. Okay, let me get rid of that now. So that's the angle, okay? And we divide this line into, let's say, 3 parts because we want to get 3 angles. And then, of course, we need to use the quadratrix to divide this circular arc into 3 equal parts, as you see here, okay? So you see 0.375, they're all got that length, okay? And how we do that is by running a line from the center, this center here, the black point, through this point to the circle arc. This is a circle arc, okay? And that's how we divide them. So that's, the Sectrix tells us how to divide an arc into equal parts. And then we just join these lines up, and we've got the equal angles, and all of these angles here are equal. So it doesn't matter how you do it. And if you go down here, you'll see they're all 30, right? That makes sense. Okay. Then the quadratrix is a kinematic curve. Okay, so what does kinematic curve mean? Okay, it means that you can start at one point, right? Like that. And if you've got, let's say, 3 partitions, it means that you can move that point there along, like so. And this distance here at the bottom from this red line to the origin is 0.333, and the next one is going to be 0.666, okay? 0.666, and the last one is going to be 1. So that's how you divide the line segment here into equal parts. And then, of course, the kinematic curve, as I'll explain to you in a moment, is done geometrically, not through this algebraic equation that you see over here. Okay, it's totally geometric. So we'll get to that in a moment. And then what you need to bear in mind here is that when you find these circular arcs, you're using the quadratrix, okay, to find the circular arcs. And by being able to find the circular arcs, you can divide this angle into any number of equal parts that you like. And let's see now how to construct a quadratrix from scratch. Okay, so first of all, what you have to remember is that when you're constructing a quadratrix, you're actually looking at a kinematic curve which has a constant rate. And a lot of people don't understand the word rate or what it means. I'm going to put an article. I have an article on my site here, which is called Exactly What is Rate? Okay, I think it's that one. Let's just say exactly rate and see if it finds it. Let's say exactly. I've got plenty of exactlies here, so let's just see if I can find the rate one. I should have done that beforehand. Here you go. So I'm going to place a link to this article where I show you what rate means and how it evolved. Okay. Coming back to this, you're looking at the rate of a circular arc to the radius. It's the same concept here. So this arc increasing at 3.36 to 0.333, okay, as you see down here. That's what you're doing when you're creating the, so if you're doing this at a constant rate, then you'll have something like this, right? And what you do is you just simply move that, and this point here in the middle draws the curve. So if you want to see the actual curve, let's just put a trace on this, and you'll see the curve, and that is the quadratrix, okay? That's how you construct it geometrically. And that is how you would know where to join, put the points on the quadratrix, and then join the line from the center to each of them, okay? Like so. If that makes any sense, okay? Then that's the constant rate. And of course, if you're looking at, let's say, a rate of pi over 8 to a quarter, that means you're dividing this circular arc, which is pi over 2, you're dividing it into four equal arcs. 1, 2, 3, 4. Okay, and it would be the circle arc, which is from here to here over this distance. Okay, this distance. So let me see if I can draw that properly. So it would be this arc to this distance, and then it would be this arc again to this distance. So it's a constant rate. Okay. Now, it doesn't matter what constant rate you choose, you'll always get the same result. Okay, so let's see here if we put on this diagram. I should have made it so that let's leave that in there and then do this. Okay, and as you can see, the blue dots are on there, and also the blue dots are on there. So it doesn't matter what rate that you choose, you will always get the quadratrix. And if you want the actual function of that curve, it's this curve down here, okay, in Cartesian representation. Of course, the Greeks didn't use that. They had a far more difficult system. Right. Then, what is a Longitudotrix? So, let's see, what is a Longitudotrix? A Longitudotrix is something that I made up. In effect, probably to pronounce that correctly, it would be Longitudotrix. Okay. Anyway, and it's something that Newton was messing around with when he was deriving the arc length of a particular curve. Okay, and so the Longitudotrix is arc length by area. Okay, it's not area by ordinate; it's arc length by area. So if you come back here and you calculate, let's just see if I can just bring this down a bit. So you'll have this curve here, which is simply it's simply this equation here, where you take the parameter, which is AL, and the function is the square root of AL squared minus X squared. So it's just a hyperbola. It's not a parabola. I think it's a hyperbola. Okay, like so, like you see inside here. And it has asymptotes at whichever point you choose to be the circle radius. So in this case, it's 1, but it may be anything. And you'll find this again on Academia, and I'll place a link to it. But of course, more important than what Newton did in his complicated arc sine derivation, as you see in front of you here, all this nonsense that he did, I've simplified this for you in the ancient Greek formulas, where you don't use radians or arc length at all. In fact, you don't even need to use a circle with these new trigonometric functions. Nobody revealed them before me, but they're based on similar Greek ideas where a chord was used. I would not be surprised if the Greeks knew of this, even though it has never been published. Okay. Well, some Greeks knew of it, not all of them. So that's pretty much how to construct a quadratrix, as you've seen here. I've shown you what the concept is. It's a constant rate. And I've talked a little bit about the different curves and what their functions are. Some are to find area, others are to find arc length. And that's pretty much it. So this is all interesting information because it was done at a time where we didn't have tools like the Cartesian system, okay, and of course representation of equations using Cartesian coordinates. A huge quantum leap in mathematics thanks to the French mathematician Descartes. I mean, the Greeks had this, but it was far more difficult to learn. Okay, and I mean, in order to learn what the Greeks were doing, you would have to probably have an IQ of above 140 in most cases, right? They were exceptionally smart. And Descartes made it possible for many more people to learn mathematics in far simpler ways. So I'll place links to all these things and to these applets if you're interested. If you're not already a subscriber, become one. Click like. Tell your friends about it. Become a follower in academia. I have plenty of articles that you can download and enjoy, and 3 books. Okay, the best books ever written. One on number, another one on the origins, the non-fiction origins and history of calculus, and another one which is actually just a collection of papers on the single variable new calculus. I'm John Gabriel, and this is a New Calculus channel. Till next time, goodbye.